capacitors. So what we'll see with capacitors is that we're following the same rules. They're just slightly different because instead of currents, I'm going to be talking about charges. So looking at capacitors, if we jump into it, again, my junction rule is going to start with this idea that I've got this conservation of charge, right? Before it was whatever flows in must flow out, and that gives me a nice statement. Here instead what we're going to use is that concept that whatever charge is building up must have been split from a neutrally charged conductor. And so we'll use that same logic to get this statement that the sum of the charge around any junction must be equal to 0. You'll see what this looks like in a minute. This may seem a little bit weird. And so for example, if I take this circuit, I would start by mapping out the signs of the charges that I think exist. So typically what that means is that this is a positive terminal on the battery, and that this is a negative terminal on the battery, and then I'm going to follow that around, right? So again, the logic would be this is going to push positive charges away, so that's positive, that's negative, right? Because this is negative, it must be, pushing the positive. And so I think that would mean that these should be positive. These should be negative. Because that's negative, that should be positive, which means that that's negative, and these match that. So it looks like I did it just fine, right? So I'm just mapping out what I think the charges are. I would then need to assign what the charge is for each of those capacitors. So I'm just going to call the charge on this Q1, the charge on this Q2, the charge on this Q3. Now here's where things get interesting. We should be okay with the idea that the charge on this is the same as that because they're in series, right? And so that means that this is also Q2. Make sense?
Yes.
Now I can use my junction rule. And the way that I do that is I start by saying, well, here's a junction. I'm going to call it A. There's another one down here. I'll call it B. And so what I'll do is I'll say for that junction A, I've got on this side a negative Q1. Cool with that? On the other side, I've got a positive Q2 and a positive Q3. Those all need to add up to 0 because, again, the logic is that this wire here was neutral. And so I divvied up the charge there, but it should still add up to 0. So the statement that I'll get hold on a minute. So the statement that I'll get is that minus Q1, because this side that's closest to the junction is negative, plus Q2 and Q3 are both positive. Those have to add up to 0. Cool with that? Now when you look at this other junction, B, you find basically the same thing. Now this one's a little bit funkier because I have to follow this line all the way back around and I see that it's the other side of Q1. Does that make sense? So what I'm really looking at is that this charge, and this charge all have to add to 0. And what you'll get then is that positive Q1 minus Q2 minus Q3, because I'm on the negative side of those capacitors now, that all has to add up to 0. And if you're paying attention, that's the opposite of that statement. Or really I should say it's the same statement, but with all the signs flipped. Does that make sense? And so again, similar to what we saw with the junction rule before, not every junction gives you new information. Because basically when I look at junction A, it's the same statement I get for junction B. Does that make any sense? Mm-hmm. So similar to before, what I'm trying to do is I'm starting by determining which way the current is flowing, right? And then I can use that direction as long as I'm consistent, I keep working through. Notice a similar thing developing here, right? I'm going to start with determining what the signs for all the different capacitors are. And then the junction rule is saying, well, everything that touches this junction, the charge on those capacitors must add up to 0, so write a statement for it. Does that make sense?
Mm-hmm.
Okay. Oh man, I was hoping that text would stay. Now, Kirchhoff's loop rule follows the same logic as before, which is saying that around any closed loop, the current has to add, the voltage has to add to 0. Except now I'm calculating my voltage just slightly differently. So remember that our capacitance equation is that the capacitance is equal to the charge per volt, basically. And so that means that the voltage is going to be equal to the charge divided by the capacitance. So whereas before when I used Ohm's law, every voltage drop across a resistor was IR, now it's going to be Q over C. Does that make sense? Mm-hmm. Now, let me tell you, for the purpose of putting these into your system of equations, I would actually prefer to probably write it this way, so that when I write in for all of my equations, I'll put 1 over the capacitance as my coefficients. It just makes it a little easier to look at that way. Does that make any sense?
Yeah.
All right, so as I go through here, it's the same reasoning, same logic. You're going to draw your loops, you're going to focus on the direction, and here's what we're going to say, right? So what I should see is that from a positive to a negative, that should be a voltage drop. And from a negative to a positive, that should be a voltage rise. And so I'm following the same logic as before. If the loop agrees with the charge change, then I count it as a drop. If it disagrees, then I count it as a rise. So it's the same logic as before. And so when I go through, that's what I end up doing. Does that make any sense? By the way, I forgot about this. I'm going to change it from last year. This has like a typo because that should be flipped in the picture. Like they changed the language, but they didn't change the picture. So in the picture, this is what I get for taking things off the internet. It should be, come on! Minus, oh my God. Can you just not be a piece of crap for like another week? All right. So when you go from positive to negative, we're going to count that as a drop in voltage. When you go from negative to positive, we count that as a rise in voltage. And that should be easy to remember because that agrees with the rule we use for the batteries. Right? Does that make sense? So as you go around the loops, you can write your equations out that way. We good with that? All right. So then the step-by-step thingy follows the same rules. So notice that when I wrote this last year, I forgot to change it. I'm first not going to map out the current flow. I'm going to map out what I think the signs of the charges on the capacitors is. Okay, and again, it's okay if you get one of these wrong. It's not a big deal. Your equation will just correct it for you. So when you get it out, if you thought the charge would be positive, but it comes out as a negative, that just means you had it flipped. It's not a big deal. Do your junction rules, do your loop rules, select your equations, create the matrix, and then RREF that mo, and then you're done, right? It's the same process. I'll show you a quick example, and then we'll call it a day. So let's go back to this guy. I would start by mapping this out, which I'd already done, but then I had to change it. So let's say that that's the positive side. Oh no. Positive side. Negative side. Whoopsies. So then this is positive, because it's going to agree there. That's negative, which should make these both positive, which should make these both negative, which should make this positive, which should make this negative, and that agrees with negative over here. So I think I did a good job. It's all fine. Cool? Next thing I'm going to do is I'm going to label all the charges. Let's do this in green, actually. So I'm going to label this as having some charge Q1. This is having some charge Q2, and I already talked about that these should be the same charge because it's in series, just like the current through both of the things in series is the same. And then this I'm going to call Q3. Cool? Oh, whoopsies. Thank you. 2. Good? So I've already got my junction rule there. I could have done one for the other junction, but remember they're the same thing. So I've covered that bit. So now what I'll do is my loops. So I'm going to do a loop here. I'm going to call that loop 1. I'm going to do a loop here and call that loop 2. And then you do a big loop all the way around. I'm going to call that loop 3. So remember the rule here is basically just think about the battery. If I go from minus to plus, that's a voltage rise. Doesn't matter if it's a capacitor or a battery. Minus to plus is a voltage rise. Plus to minus is a voltage drop, and then I'm going to use that statement 1 over the capacitance times Q to represent the voltage rise or drop respectively. We cool with this? So let's go through my loops. I'll start with loop 1 where I first hit the battery. So that's a voltage rise. It's from minus to plus. And so I'm going to put that in as 10. I follow the loop around, and now I'm going from plus to minus. So that's a voltage drop. And that voltage drop is going to be minus 1/20th of Q1. I'm just using this, right? The capacitance is 20, so I'm putting in 20. Cool with that? Okay. Keep following the loop. I've got another plus to minus, and so I'm going to put that in as a voltage drop. The capacitance is 60, so I'm going 1 over 60 times Q2. And then notice I follow and I see one more here along my loop. So I'm going to put minus 1 over 40 Q2. And then I keep following and I get back to my battery, so that must be equal to 0. Now I want you to notice something here we didn't see on the last thing, which is that I've got two Q2s here. So before you go put it into your matrix, those are going to have to be combined, right? So you just combine like terms. 1/60th plus 1/40th, you just add those together. I would probably put those in terms of what? 1/120ths and then add them together. Does that make any sense? And you could probably use a calculator for that. It's fine. But before I put it in the matrix, I need to put those together. Make sense? Okay. For loop 2, I'm going to follow here. What I want you to see is that both of these guys that have a charge of Q2, they're actually both, as far as my loop direction is concerned, they're both going to go from minus to positive, right? So I'm going to consider both of those to actually be voltage lifts instead of voltage drops. And so I'm going to get, in the order the loop goes, 1 over 40 Q2 plus 1 over 60 Q2. I follow it around, and Q3 is going plus to minus, so that's a voltage drop. So minus 1 over 100 Q3, and that's equal to 0. So there's another statement. Again, you'll have to put these together. Notice though I'm putting the same thing together, so it's like the same math. Cool? Then I do the outside loop, and so if I start here and go around, I'm first going to have a voltage drop. So minus 1/20th Q1. And then I'm going to follow around to another voltage drop, so minus 1/100th Q3. And then I follow it around and I hit the battery, so plus 10. And that's equal to 0. The battery's plus because I'm going from minus to positive. So remember, when you're looking at capacitors, it's all about minus to positive is a voltage rise, plus to minus is a voltage drop. Make sense? Now I've got my I've got 4 statements. Remember that I've only got 3 charges, so I really only need 3 statements, so pick one to forget about. And again, notice that these two both have Q2 in there twice. So I'll need to collect those terms together, put it in the matrix, let the matrix solve it. I would recommend just putting these into the matrix, by the way, as fractions. So just put them in as, 1 over 100. I'm not sure what that'll come out to there. What, like 3 over 120 plus 2 over 120, so like 5 over 120 Q2? Just put it in as 5 over 120. Does that make sense? Mm-hmm. Work with fractions. It's actually easier. Don't make decimals because then it might be rounding as it goes through and get the question wrong. We cool with that? Mm-hmm. So that's Kirchhoff's rules, or Kirchhoff's laws, whichever way you want to say it, in one day, right? So we talked about both ways that you do it. The nice thing about this is that you don't actually have to really understand anything about circuits to do this. You just have to know the process. And so that makes it a good process. However, I think if you understand the basics, it can be easier to solve simple circuits the other way because you just don't have to do quite as much work. Does that make sense? Any closing questions? Man, I finished up like right on time.
Good for you.
I know. It feels good. Okay, that's it then. I'll try and get these videos posted later today if I can.